Hello and welcome everyone. Thank you for joining us for our expert session. These are short webinars and last no more than 30 minutes, bringing you valuable insights from industry experts. Today's session will be presented by Sunny Solanki. He's a senior technical manager at I-Gard Corporation. Sunny is an electrical engineer from McMaster University with over 10 years of experience in protection systems and relays. Throughout his career, he has educated consultants and end users on the benefits of integrating electrical protection products into their design to enhance personnel and equipment safety. He specializes in providing commercial and technical support for various projects and applications, including high resistance grounded systems, low resistance grounded systems, hybrid HRG systems, arc flash protection systems, and personal protection products. We are excited to have him here today, and we appreciate your participation. Without further delay, I would now request Sunny to take over from here.
Thanks, Devansh. Today's presentation is going to be on transformer protection and surge mitigation. So let's start by talking about transients. So a transient in an electrical system is a short duration, rapid disturbance in voltage or current that arises when the system's steady state condition are abruptly altered by switching operation, faults, or interaction among inductive and capacitive components. During energization, transients can produce very high frequency oscillations between 100 kilohertz to 10 megahertz, as energy is exchanged between supply and load capacitances for only a fraction of a millisecond before steady load current develops. On de-energization, transients occur when a 50 Hz or 60 Hz load current is suddenly interrupted, leaving residual current trapped in the winding. This energy then transfers into the load capacitance and oscillates at much lower frequencies, typically between 1 to 10 kilohertz. So these transient behaviors are inherent to medium voltage systems and are critical to understanding how switching events impose electrical and dielectrical stress on connected equipment. Now, when we discuss the types of transients, we already discussed the energization and de-energization transients based on the previous slide. There's also switching devices that can also generate mixed transients, including pre-strike events where premature contact ionization produces steep wavefront surges, current chopping when an arc forces the current to break at a finite value, restrike caused by dielectric breakdown after interruption, and multiple restriking a repeated chop. Restrike sequence producing 4 to 6 PU surges with sub-microsecond rise times. So very, very steep, high, um, high peaking values in just a short duration of time. So, as described in our ZORC manual, these steep wavefront surges can be between zero point 0.1 to 2 microseconds in terms of its rise time, and are intensified by reflection and refraction at the motor or transformer terminals due to surge impedance mismatch, often doubling the incident voltage as these two signals meet at one point. And stressing line and coil insulation. They might also arise from lightning, arc faults, or virtual current chopping. So here's an example of pictures of where insulation was breaking down due to switching transients. And you could see that eventually, once the insulation breaks down from the conductor does have a path, um, in a sense, to a ground fault. Um, or potentially even a face-to-face failure, depending on the type of failure you're experiencing. But this transient activity, it's definitely going to impact the useful life of your electrical equipment. And there has to be something that we can do to attempt to suppress these transient overvoltages. So surge suppression is a method of limiting these transient overvoltages or absorbing or reshaping the fast high magnitude voltage spikes so that they cannot overstress motor, transformer, or generator insulation. So in practice, we achieve this through several methods. The first method is surge suppression, where we prevent transient overvoltages from overstressing motor, transformer, generator insulation. Surge arresters can clamp high magnitude impulses to a safe voltage level and are typically really good for lightning strikes. We have RC snubbers, which absorb transient energy and slow steep wavefront times, and cable terminating resistors to reduce the surge reflection and voltage doubling at load terminals. We have high frequency suppressors, so devices like ZORC, which can try to mitigate the very, very high frequency um, surges that come into the system by using a zinc oxide element to eliminate pre-strike and restrike events and keep surges within IEEE and CIGRE insulation limits. Insulation coordination, so combined methods lower surge magnitude, slow rise time, and reduce high frequency stress on equipment insulation. So right now, for most part, we see a lot of surge arresters in the industry. Surge arresters typically have a spark gap between 2 points, and in normal operation for the system, this spark gap acts as an open circuit, so no current is really flowing through this spark gap in normal operation. But when a transient occurs, there's an electrical breakdown between the air between these 2 points so that um, the energy from the transient can be diverted to ground. Similarly, for the surge capacitor, we see that in normal operation, it has a very high impedance. But when we experience a transient, we see that this can become a short circuit and then that energy can go to ground. With the addition of a resistor as an RC suppressor, we can reduce the wavefront magnitudes to a value that we dictate, and that way we can match the impedance so that we can reduce this doubling effect of these transients from escalating to higher points and reduce the restriking capability. The capacitance is typically ahead of the resistor so that you can block out this resistor from impacting during normal operation. And then when the capacitance uh, is seen as a short, when the transient's coming through, then this resistor will be able to limit the magnitude of that transient and bring it towards ground to be dissipated. Now, the zinc oxide RC snubber has a zinc oxide component, and this zinc oxide component really helps when there's really high frequencies, such that the resistor will not heat up as much, and this becomes the faster path to ground. So it's a means of protecting the resistor and also making sure that high frequency transients are going to be directed to ground instead of impacting the rest of the system in order to protect it. So for surge arresters, their characteristics are they have slight limiting of surge magnitudes, so approximately 3 pu, no effect on surge rise times. It does not limit voltage doubling, and it's inadequate surge protection from escalating voltages caused by circuit resonance. Surge arresters are really good for lightning strikes, but aside from that, for switching transients, it shouldn't be the preferred method. For surge capacitors, we reduce the escalation of peak pre-strike voltages, reduce the number of pre-strikes, but because the surge capacitor is undamped, you may enhance the high frequency capacitive coupling, and it could increase severity of stalled tripping surges. Now, at RC suppressors or snubbers, we match the surge impedance of load cables using the resistor, reduce reignition surge voltages. Unfortunately, it does not limit surge rise times. It cancels the voltage doubling effect by utilizing the resistor, and it's best installed at terminals. Now, the zinc oxide RC snubber can be installed at either end of load cable. It's both frequency and voltage dependent because we're able to handle those very, very high frequency transients. It's discharge free at full system voltage and it eliminates sequential reignitioning. So the benefits of the ZORC is that it has surge control. So ZORC reduces steep wavefront magnitudes, eliminating voltage doubling effects, and suppresses pre-strike and restrike behavior by matching the cable's transient surge impedance. There's transient elimination by removing high-frequency reflections and preventing current zeros in the switch contact gap. ZORC stops multiple pre-striking and restriking events. Surge limiting, so ZORC enforces a defined upper limit on steep wavefront surges and reshapes any excess to maintain safe insulation stress levels. And that's where insulation coordination comes in. So it maintains full insulation coordination across all practical surge magnitudes and rise times, keeping stresses within IEEE motor withstand curves. In terms of equipment protection, ZORC protects new motors and dry-type transformers by lowering surge magnitude, rise time, and occurrence frequency throughout their service life. So the ZORC is essentially acting as the fall guy for your higher cost capital equipment. So large motors, transformers, generators, and are very like high capital cost. And on top of that, could have very long lead times. With the ZORC, you're basically diverting the power from the phases to ground when there's a transient occurring, and it's acting to kind of reduce these steep wave fronts and be the one where all of that transient basically gets redirected through the ZORC to ground. So when you retrofit a ZORC, you're reducing the cumulative transient stresses on your system and you extend insulation life in existing machines. And that's where the cost savings come in. So you're preventing insulation failures on critical equipment. So ZORC avoids repair costs and the far greater financial impact of downtime and loss reduction for critical equipment, such as your motors, transformers, generators. So let's take a look at this graph here where we have a graph on the left side without the ZORC. This is on a 12.47 kV system. And from top to bottom, each of these rectangles represents 40 kV. And from left to right, we have 1 milliseconds per div. So you could see that we experienced a 40 kilovolt peak TRV at a 50 amp switching current, and that lasted for a duration just over 2 milliseconds. So we want to mitigate this switching transient as the system is coming online. So this is happening during energization. Now, when you have a ZORC in your system, for that same 12.47 kV system, we're seeing that we have 6.2 kV peak TRV, and then we are mitigating this transient overvoltage that we would see on the left side at 40 kV. So how the ZORC works, so during low frequency behavior in normal operation at 60 Hertz, the capacitors have a very high impedance and it keeps the resistive path out of the circuit. So you saw that the capacitance was above the resistor and the zinc oxide portion. So right now it's acting as the blocker to stop any current from going down to ground. The high frequency behavior, so during transients, their impedance drops, inserting the damping network into the system, which consists of the resistor and the zinc oxide portion. And then wavefront control, this minimizes reflection, prevents voltage doubling, and removes high frequency current zeros that cause multiple pre-strikes and restrike. So when the zinc oxide is activated under large steep surges, the zinc oxide arrestor conducts to limit and reshape the wavefront. The impedance choice of 30 ohm resistor suits most installations because cable surge impedance is largely independent of length, motor size, or voltage. Optimized capacitance. Capacitor values are selected to limit heating and stress on the resistors. Typically, from what I've seen in the industry, we have a range of 0.15 microfarad to 0.3 microfarads. And we also have gapless zinc oxide suitability. So gapless zinc oxide arrestors are used because they see negligible voltage under normal operating conditions. The features of the ZORC is that it's a very compact design, so small enough to fit inside most motor, transformer, or switchgear terminal enclosures. It's very low cost in comparison to the other equipment in your electrical system. So it offers a strong price to performance ratio for protecting the more critical, higher cost equipment. It's easy to apply. It can be selected directly from a catalog with no detailed engineering. Flexible mounting, so we can mount in a motor transformer with our M-type, or we can panel mount with our P-type variants. We can also supply enclosures with like NEMA 1 or NEMA Type 3R that would include 3 ZORC units, 1 per phase, or 1 3-phase ZORC inside of an enclosure. So we have the phase options, which I discussed, which are single phase and 3-phase. Most of the lower voltage units will come as a 3-phase unit, but as we get to the higher voltages, we need more kind of distance between each of the phases to reduce electrical tracking. We also have hazardous area suitability, so optional certification for Class 1 Div 2, non-sparking environments, and temperature classes T1 to T5. Very easy to install, so it's mountable in any orientation with provided brackets or clamps. And it's proven to be reliable because we have thousands installed over decades, reducing installation failures and downtime across motors, generators, and transformers. So right now in our offering, we have standard ZORCs between 2.2 kV to 40 kV. We're also working on compact ZORCs between 3.3 and 6.6 kV. These ZORCs include the resistor component, the capacitive component, and the zinc oxide component. We also offer low voltage RC snubbers between 400 to 1100 volts, which would only include the RC portion. RC snubbers between 7.2 to 40 kV. We have compact variants between 3.3 to 6.6 kV, but we're hoping to get more compact units out on higher kV levels, but we're still working on it. We have high voltage RC snubbers between 25 to 40 kV, and that would be basically the summation of our offerings. Now let's go into the questions that you guys may have, and we'll be able to address those right now. So let me just, there we go. All right. What are the red and yellow lines on the graph on the previous slide? Are you talking about this graph? Well, let me see. Red and yellow, okay. So I believe that the yellow is your phase voltage, which is what's causing that high level of transient overvoltage. The C2 line, I'd have to inquire on that one. But I'm mostly focusing on the yellow line where we're seeing a lot of high switching transient for that short duration of just over 2 milliseconds. Yeah. Do you have any pictures of the device installed? I can share pictures of the device installed with you. Please send me an email to my email and I can get you pictures of how this unit is installed. Questions? Is installation coordination relevant for equipment that are rated below 25 kV? BIL for these equipment are often quite high. I would say it should still be relevant, but I can inquire with my VP of engineering to see what he has to say about that. I'll quickly, if you can just send me an email on that, I can get you something on that for sure. We're going to be sharing the presentation slides as well. Do you have any statistics for transformer failure rates when protected from switching transients from ZORC or RC snubbers versus no protection? I understand the savings versus a failure, but we have clients that are weighing first cost versus a theoretical future problem. What I can say to that, Brian, is we pay for insurance, but we don't always use it. But it's good to have because if something goes wrong, then at least you're covered. It's tough to underlie the financial justification, even though you're not even sure if you have switching transients. But as I mentioned before, you have energization transients, which can be very high frequency for a very short duration. And then you also have de-energizing transients. That includes even if, let's say, you have a solidly grounded system and a ground fault occurs and the feeder breaker isolates itself, that's still a method of switching out a certain amount of capacitance from the system that particular load was contributing to the overall system. So there may be some switching transients of units being switched out of a system as well. So in that case, it all comes down to whether you want to take the risk without it or if you want the insurance there, then you would provide something like this. So case by case basis, but yeah. Can you please explain what RC only means in the table you showed earlier? So for RC, it just involves the capacitor and the resistor. And that's the standard surge suppressors that were used in the past. But now a lot of modern surge suppressor units include a zinc oxide portion, which is like basically a variable resistor that is intended to handle even higher frequency transients better than the standard RC snubbers that are on the market. Does this work with VFDs or are there technical issues? I've seen some VFDs have surge suppressors on them, but I am not sure if it can mitigate in relation to harmonics per se, but definitely just the switching transients it'll be able to handle. So zinc oxide RC snubbers are not designed to mitigate harmonics like it's a filter. It's more about switching transients. It's possible it can work with VFDs, but I am not sure, to be honest. Was the graph a manual switching event or automated? I will inquire with my VP to see. Please send me a message on my email and I can get back to you on that. Do you need to be coordinated with relays? No, you don't, because this is like, we're talking about very low milliseconds. So I don't think that this involves relay coordination. It's more so about just having it interconnected in your system to handle those high frequency transients when they come in. Hand versus spring or motorized? I'm not sure. Do you have single phase snubbers for each phase for a 3-phase transformer, specifically when it comes to higher voltages? Yes, we do. We have single phase variants and we have 3-phase variants for voltages above 15 kV. You described the old arc gap arrestors. Today, most arrestors I see are metal oxide type. Yeah, I just explained from like a very generalized point of view, but yes, I agree with you. Most are metal oxide for the arrestors today. Will a nearby lightning strike destroy a ZORC? I'm not sure on that either. I will have to probably get back to you on that one. I mean, I think lightning can do a lot of damage, so. Can you share the presentation? Yes, we'll share the presentation. We'll share the catalog. What is the typical lifespan of a ZORC? How many interruptions can it limit before it needs to be replaced? I think what you need to do is mostly do an annual inspection of the unit, make sure that there's no bulges in the enclosure, do some testing on the capacitance from one side to ground, and make sure that it's within the tolerance limits. These are all covered in our manual, and we can provide the manual to you, Joseph, if required. But in general, it's mostly about making sure that the ZORC is still intact, because the ZORC is considered the fall guy. So I'd imagine maybe after a few adjustments for transient overvoltages, you may have to replace one of the units, because you may be seeing bulges, or your pressure sensor on the unit, which is controlling the pressure inside of the enclosure, is alarming to you. Then that would be a cause for concern to address that you need to replace that ZORC. Is this ZORC to help voltage sag issue? I don't think so, Andrew. Maybe I missed this part in the presentation, but how do we have the certainty that the ZORC is actually doing its job? You'd have to be looking at waveforms before and after, I would assume, to say that this is doing its job. But some of the PS CAD models that you would have to simulate transients would indicate that you would need a product like this to mitigate those transients based on what you're simulating. For transformer dry type protection, if you have an RC snubber, do you also need a surge arrestor for lightning protection? What I've seen in the industry is they actually use these in parallel with each other. So you would have an RC snubber in parallel with a surge arrestor. Surge arrestor handles the lightning protection. RC snubber is good for the switching transients that occur when you're energizing and de-energizing. So a combination of both would be achieving full level of protection for the switching transients and the lightning protection. That would be my recommendation. What would be the passive effect from ZORC for the system? Mostly what we're trying to do is, because that capacitance in normal operation is very high impedance, there's very minimal effect from the ZORC in the system, because the capacitance is blocking out majority of the current from flowing through it to ground. So I think the effect is very minimal for ZORC on the system in normal operation. What kind of commissioning test you do to certify the system? There are a few steps that you can take once you've connected the unit, but those are outlined in the manual mostly. I don't remember them off the top of my head, but I can share them with you if you write an email to my address. I think you have my email already, so send your email and I'll try and send you something on the commissioning tests. All right, I think that's it. Thanks for everyone for coming out to this presentation. You guys had a lot of great questions, also stumping me on some of them. But feel free to reach out to me on my email. My email is going to be right here. And I'll try and get back to you as soon as I can. And I hope you guys have the great rest of your day. And I think our next one is going to be on June 24th for load banks. So stay tuned for that one. Thanks a lot. Have a great day. Take care.